Alright, so starting out, this section is applying theorems in calculus. So we're going to talk about the intermediate value theorem, extreme value theorem, Rolle's theorem, and the mean value theorem. So all of which we have discussed at some point, whether recently as in last week or prior weeks, but we have talked about all four of these. So before we actually go and use these and apply these in problems, we just want to remember what the definitions are, restate them. That way you have all four definitions on one piece of paper. When you're studying, going through homework, you have them there and you know where to find them.
I have the next unit so I can put out these kids on that. For pre-cal.
Yep. So the first one is the intermediate value theorem. So although it may not be a formal definition, who can maybe remember what the intermediate value theorem is, what it says, how we use it? The intermediate value theorem. Do you remember anything about it? Okay, we first know that f of x, so if f of x is continuous on closed interval a to b. Does that help anybody? Intermediate? Froze. Thank you. If f of x is continuous on some closed interval a to b, do we remember the intermediate value theorem at all? Been too long? Not sure? 3-day weekend? Okay, I'm going to state out the actual definition of it, and then I'm going to state how it was in some of the problems we applied it to. So if it's continuous on AB and f of A is less than y, which is less than f of b, then there is at least one value of c on AB, and that's the open interval, such that f of c equals y. So this is the formal definition here. If it's continuous and you have f of a is less than y, which is less than f of b, there's at least one value c on that interval between a and b that f of c is equal to that y value. Does anybody remember the application we applied this to? We didn't say y necessarily. What did we use? Some of the problems we talked about, we used something else instead of y. So we had stated if f of a was a negative number and f of b was a positive number, so less than 0, greater than 0, if we have 0 in the middle, then there's at least one value c such that f of c would be equal to 0. So if we know the interval is continuous from a to b and this one's less than 0 and that one's greater than 0, it has to cross the x-axis somewhere. So at some point in between there, there's some value c where if you evaluate it, you're equal to 0. So that's how we had used the intermediate value theorem, determining if there was a 0 between 2 points on a continuous interval. This is the generic formula saying that if you're just between some 2 points, there's a y between there that's guaranteed to be in between a and b, where f of c is equal to that y value. Do you remember using the intermediate value theorem that way, with the 0 being in between? Alright, so the next one is the extreme value theorem. The extreme value theorem, does anybody remember that before we write out the definition? Extreme value theorem. What do you think of when you think of extreme values? Maxes and mins. Okay, so let's look at the definition then. If f of x is continuous on AB, closed interval, so at least that's the same as the first one, then there must be an absolute max and an absolute min. So we're saying if that interval is continuous there must be an absolute max and an absolute min. That's the extreme value theorem. We're talking about the extremes. Absolute max, absolute min. Alright, very good. Bless you. The next one we talked about last week, Rolle's theorem. Does anybody remember what Rolle's theorem says? Need to look back, go ahead, remind yourself. Anybody remember? At least the idea of it?
It has to be continuous and differentiable.
Okay, that's true. That's a big part of it. So if f of x is continuous on the closed interval a to b. So what have we noticed so far about the first three definitions? They've all started the same way. So if f of x is continuous on the closed interval a to b, this one is then and differentiable on open interval a to b. And f of a what? What's the next part? F of a, do we remember? Equals f of b. Then there is a value c on the open interval ab such that f prime of that value c must equal what? 0. Very good. So if f of x is continuous on the closed interval a to b, differentiable on a to b, and the endpoints f of a equals f of b, remember those endpoints are the same, there's a value in there, c, on that interval where the derivative is equal to 0. That's Rolle's theorem. All right, the mean value theorem. How do we think this one's going to start? If f of x is continuous on the closed interval a to b. And so this is the last one we did. We did this on Friday, the mean value theorem. Continuous on a to b and what on the open interval? Differentiable. Differentiable on open interval a to b. Then there is a value c such that f prime of c equals, so remember what this one, mean value theorem. Think about what we just wrote. Think about what that means. Try to think about all the way back to Friday those problems we talked about. That is saying the derivative is equal to what? The derivative at that point c is equal to what? And do you remember what that actually was finding? You are correct. This is a tangent line, slope of a tangent line. Do you know what this was? Yes, slope of the secant. So we're saying that the slope of the tangent line at that point is equal to the slope of the secant line at the endpoints. Exactly. Very good. So that's what the mean value theorem is telling you. Another word for mean would be average, if you want to write average value theorem. All right, so those are the definitions. Again, you have them all in one place now, so you can refer back to those statements. They'll help you in the following problems. So let's go ahead and go to the back. All right, so this first problem here. The rate at which water flows out of a pipe. So we're talking about water flowing out of something. In gallons per hour. That sounds important. We'll go back to it, but I'm just going to box it right now. Is given by the differentiable function. Well, differentiable sounds important. R of time t. The table below shows the rate as measured every 3 hours for a 24-hour period. Okay, so we know water's flowing out, and it's flowing out in gallons per hour. Gallons per hour is an example of a what? A rate. Very good. That's a rate. And a rate you can find by doing what with the original function? How can you find a rate?
Find the slope.
And how do you find the slope? You're correct.
Y2 minus y1 over x2 minus x1.
I don't want to find it that way. That would be the algebraic way. I want to find like the calculus way of finding slope of an original function. I mean, you're correct with what you've said so far. If I give you a function and I say find the slope at this point.
Derivative.
A derivative, yeah. So the rate, so this is just AKA, also known as the first derivative. So this gallons per hour, we're talking about the first derivative here. Okay. Now think back, it's been a few sections back, but think about differentiability. If it's a differentiable function, what else do we know if it is differentiable? Yes, it's continuous. Remember, differentiable implies continuity. Continuity does not imply differentiability. So it's continuous too. So that's important. We know it's continuous too. So if you look, they don't give you the function, they give you the table represented. So you can take a second, look at your table there. They give you the T for time in hours. They told you it's from 0 to 24. And they give you the rate in gallons per hour there. All right, so part A. It says estimate the value of r prime of 5, indicating correct units of measure. Explain what this value means about r of t. Okay. So now I think we want to kind of think along the lines what Braden was thinking earlier, but how are we going to estimate the value of r prime of 5? Do they give you a value of 5 in the table? No. So they truly do want an estimate because we don't know what it is, but how? We want to find r prime of 5. We want to find an estimate for that. How do we find the estimate at that point? Again, think about what we know. We know it's differentiable. We know it's continuous. We want to find the slope. We want to find the estimate of the slope at that point. Okay, so how are we going to use that?
Use 6 and 3.
Exactly. So if you think of your mean value theorem, we know it's differentiable and continuous, so we can use the points here and the points here to find the slope of 5 in between. So this would be the slope between R3 and R of 6, which equals, and we're going to use the mean value theorem as Braden said. So if you evaluate it, let's just say it's a function f, I think, it says function r. So R of 6 would be 10.8. R of 3 is 10.4, so you subtract those, over b minus a, so 6 minus 3. That's applying the mean value theorem. Go ahead and get your calculator and find out what that value is. You're going to get a decimal. Did anybody get the decimal value? All right, Vinny?
0.1.
Okay, good. So that is our value, 0.133. Do you have the units yet or no?
No idea.
Okay, so we need to figure out the units. This is very important here to include your units. So think about what we found and figure out what the units are. Go ahead.
Would be gallons per hour squared.
Yeah, gallons per hour squared. Because we're talking about the slope of that derivative. So gallons per hour squared. Very good. All right, so it says this is the rate at which water is flowing out. So water is flowing out of that pipe at what kind of rate? Water's flowing out of that pipe at what kind of rate? If you would think about something, it's emptying something, you could think of it that way. But it's coming out, think about your answer you got, it's coming out of that pipe at what kind of rate? We're talking about the rate of the derivative. So, it's coming out of the pipe at what kind of rate? We're going to write out, so let's start, and then you can think about it more. The rate at which water is flowing out of the pipe is what at t equals 5 hours. So we're looking for some blank. Okay, Daniel?
Would it be increasing?
Yeah. So it's a positive answer, so the rate is increasing at that point. The rate at which the water is flowing out of the pipe is increasing at t equals 5 hours. Exactly. Very good. All right, let's go to part B. Same question here. Using correct units of measure, find the average rate of change of r of t from t equals 3 to t equals 18. So, what do you think we're using here? Should seem familiar. Yeah, mean value theorem again. So, we're finding the average rate of change. So we're finding r of 18 minus r of 3 over 18 minus 3. And again, if you use your table to help you out with this one, you would get 10.7 minus 10.4 over 18 minus 3. And you are going to get some decimal again. So again, we're using the table to help us find those values. So this time we were talking about 18 and 3. Who has the decimal? 0.02. And don't forget units. Or units are what? Remember, it's the rate of the derivative. Gallons per hour squared. And that's all it asks for in part B. So very good. So again, we've just applied the mean value theorem twice, and we knew that we could use it from the top because we know it's continuous and differentiable from the top. All right, let's look at part C. Is there some time t from 0 to 24, so is there some time t in between there, such that the derivative, r of t, is equal to 0? Justify your answer. So there may not be any mathematical work. There could be. But think about what they're asking, think about the stipulations, think about what you know from up above, and think about your definitions, and try to determine an answer from there. So go ahead, look at your definitions for a moment, look at your table, and see what you can determine. Think about what they're asking. They're asking about this interval. There's something important about this right here. Daniel?
Yes, and we could, we'll use Rolle's theorem for this, as r of t is continuous, and it is differentiable, and RA equals RB, because if you look up 0 and 24, they both equal each other in R2. If all those are true according to the Rolle's theorem, which states that if all those things are true. If it's continuous on AB, differentiable on AB, and FA equals FB, then there has to be at some point an FC that equals 0 or an RT that equals 0.
So exactly. So we know it's differentiable and continuous from the beginning. They told us differentiable, so we knew it was continuous. But then we have to determine, are the endpoints the same? Well, the endpoints they gave us were 0 and 24. So if I go to 0, I get 9.6. If I go to 24, I get 9.6. So I know at that point, or those 2 points, they are the same, and it's continuous and differentiable. So by Rolle's theorem, I know somewhere in between there, the derivative has to be 0. Okay, so since R of t is differentiable, which from up above, they didn't tell us continuous, but they told us it's differentiable, which implies continuity. On 0 to 24, and R of 0 equals R of 24, which equals 9.6. Then Rolle's theorem guarantees a value C in the interval 0 to 24 such that R prime of C equals 0. We knew it was differentiable, that implied continuity. The endpoints were the same. So by Rolle's theorem, we guaranteed there was some point where the derivative was equal to 0. All right, any questions? So far, we've been able to use the mean value theorem and Rolle's theorem, and we're just looking at some problem and being able to apply the knowledge of knowing the definition to help us out in the problem. So I'm going to leave this up here for a moment, but we only have a few minutes left, so we are not going to have time to go on to the next example. So we'll move on to the next example tomorrow, and depending on how much we get through tomorrow, that will determine when your quiz is. So we'll see how far we get tomorrow and make that determination on quiz on Thursday or Friday.